inverses of primary trig functions. We're going to talk about the graphs of those. This is IB only. That means it won't be on your diploma exam when we're talking about the graphs of inverse trig functions. Okay? So just be aware of that. Reciprocals, yes. Okay, on diploma exam, but inverse trig functions, no. And so obviously you use inverse trig to get angles and that kind of thing in all of the things, but this is actually looking at the graph of them. So there's just snippets of y equals sine, cosine, tan. Okay? And so if we're finding the inverse, we want to interchange x and y on every point. These graphs, just always remember, if you're trying to interchange x and y here, these scales aren't the same. This, it looks like a square there, right? But this is pi units, and this is 1 unit. So pi is about 3.14, right? So just be aware of that. If I were to say, take the inverse of this point would stay the same, 0, 0. But pi, 0, would be 0 pi, which would be up here. Right? The scale is different horizontally and vertically. So my y equals x is not going to be diagonally like that. If you're just thinking about graphing it, you'll notice on the right-hand side of the page, those ones are, the scale is more accurate. Okay? So we've stretched it out so that you can see a little bit easier. The inverse of it. Okay, so those are the original. That's all good. We know that. But think about what happens. We just said reflected in the line y equals x. We'll interchange x and y. Okay, so what happens? So if we interchange x and y, this will be x equals sine of y. We always like to show our functions as y equals. So here, if y is the argument, to get y, we take the inverse sine of x. Remember, second sine in your calculator. Okay. So this wouldn't be an angle anymore, right? This would be a ratio. Pardon? Question? Cos x equals cos y, y equals cos inverse x, x equals tan of y, y equals tan inverse of x. Okay? So this is not really a huge concept. The hardest part of this is we want these to be functions. So remember, when we want a function, it's got to pass the vertical line test. For every x here, there can only be one y. All right? So that's where, on the right-hand, well, we're kind of going to go, I'm going to move these. Actually, maybe I can do that. I'm going to move this one up here and then go dual. Okay, so we're kind of going to, before we fill in our domains and ranges, think about what the graph is going to look like. So I've kind of moved the graphs from your right-hand page next to these original ones, right? So let's do the inverse here. So notice how the scale has changed rather than going pi's here to help us with graphing, right? So this point here, if I interchange 0, 0, nothing happens. Stays at 0, 0. This is pi over 2 for x, 1 for y. So now I want 1 for x, pi over 2 for y. So I've done those 2 points. This point here, pi 0 becomes 0 pi. Okay, so you know that it's going like this. And then likely it's going to go back the other way, right? So here, this is 3 pi over 2, negative 1. So this will be negative 1. 3 pi over 2. No, what did I just say? Yeah, so it's going to be up here. Okay, so that will be off my graph. But if I go to the negative here, negative pi over 2, negative 1, and negative 1, negative pi over 2, so that it fits in this graph that I've given him, right? Okay, is that a function? What I just graphed? No. So we want to limit it so that it is a function. Okay, so above these graphs, you'll see it says, however, if the inverses are to be functions of x, then the domain or range must be restricted for each of the functions, which results in. So for sine, you could choose any parts of it and make a function. Right? I could choose, okay, this part, I could choose this part, that part, I could just do this, right? There's many parts of it that will be a function. We want the biggest part that is around the origin, or positive values. So here, if I choose this, is that red line that I drew a function? Yes. So what are my new x values? They're from negative 1 to positive 1. And then my new y values are from negative pi over 2 to positive pi over 2. So I think it's in my next screen here. Okay, let me just move this. Just give me 1 sec. Here. There, we can fill it in. So we're going to go back above and say for this new x value of negative 1 to positive 1, and from negative pi over 2 to positive pi over 2. Okay. So that's we call it a convention. That's what mathematicians have decided as the definition. Okay, so it could be any parts giving you a function, but what it's going to, you need to use to keep it a function in all cases is going to be between negative 1 and positive 1 for x, negative pi over 2, positive pi over 2 for y. So think about it as being around the origin. Okay, so now let's go back and do cosine. So cosine here, 0, 1 becomes 1, 0. Pi over 2, 0 becomes 0 pi over 2. So I've done those two. 1, sorry, not 1. Pi, negative 1 becomes negative 1 pi. Okay. If I go further, I'm going to not have graphs, so I'm going to go back to the negative here. Negative pi over 2, 0 becomes 0, negative pi over 2. Negative pi, negative 1 becomes negative 1, negative pi. So basically it looks like this, approximately. Is that a function? No. So we want to restrict it. For sine, we went about the origin, below and above. This part, if I do it like that, it's still not a function. So I want either this part or this part. And so that's where, by convention, it's going to be the positive values rather than using negative pi to 0. So it's going to be this part here. So that's for x between negative 1 and positive 1. So same as for sine. but then our y's are between 0 and pi. So -1 or +1, that's between 0 and pi. Notice this notation here. So this is the same as cos inverse of x. It's also called arc cos. So I think in the IB diploma, or in the IB data booklet, they use arc cos. On your calculator, it's inverse cos, as opposed to the -1. So just be aware that they're doing the same thing. Okay, then do the same for tan. Okay, so 0, 0 stays as 0, 0. Think about the asymptotes. So this asymptote at pi over 2 for x here becomes the horizontal asymptote at pi over 2 for y. So okay, so that pi over 2 horizontal, inverse is always vertical of a horizontal line. Of a vertical line is a horizontal. This is too much. Negative pi over 2 would become negative pi over 2 here. Okay. So our curves, our zigzags, are going to be horizontal. You think about this, pi over 4, 1, will become 1 pi over 4. Negative pi over 4, negative 1, will become negative 1, negative pi over 4. So your curve is going to look like that. Is that a function? Yeah. So you don't have to restrict the x values. It can be any x value. Okay. Now, saying that, in that, that's only one part of the graph. If I kept on going, there would be, I probably should do that. I should do the next one up here, just so you realize, okay, that actually, there's more to it, right? So that is still part of the graph. There's one down here. So each separate cycle is a function, but overall, the whole thing isn't. So we limit it to this. So x can be anything, any real number, but y is going to be between negative pi over 2 and positive pi over 2 to keep one cycle of it. Okay? And then again, why don't we choose this one? Well, we could, but by convention, mathematicians in the past have said we're going to keep it around the origin, the smallest possible values. So that's where we put in here. This can be from negative infinity to positive. So this is going to be from negative pi over 2 to positive pi over 2. And notice how there's no equal signs there. They are asymptotes. So, we're going to find some values. Or should we wait? I think we'll wait till tomorrow. Yeah. We've got enough for today. So, you can look at the examples, but we'll start on examples tomorrow. Just that last page. It says state the value of each of the following. So if you're taking sine inverse of sine, those to get back to the initial value, right? So sine of pi, or you do work from the inside out. Sine of pi over 4 is root 2 over 2. Inverse sine of root 2 over 2 is pi over 4. Alright? So they're opposite operations. Now there are other angles that give you root 2 over 2. But that's pretty easy. Right? Sine inverse of sine. Get back to the beginning. The problem is if the angle is outside of that initial interval of values. Okay? Let's go down to the next one. Now we have sine of pi over 7. I don't know what the value is, right? It's not a special angle. But if you're doing sine inverse, guys, of sine, then you'll get pi over 7. Okay? Pi over 7, pi over 4, and you look at here, these values for sine, they fall in this interval of values here. Okay? They're between negative pi over 2 and positive pi over 2. Okay? Now, this, the inverse is at the beginning. Okay? In the inside. But again, there are inverse operations. You can think about it. So, you have a ratio of 1/2. What angle gives you a sine of 1/2? Smallest positive, 30 degrees. We're going to deal in radians, so pi over 6. Okay, sine of pi over 6 is 1/2. Okay, now, next one. I'm just going down. It doesn't matter which way you go, but I'm going downwards here. So now here, notice how this angle is 5 pi over 4. Okay? Is that bigger than pi? It's bigger than pi. For sure, none of your intervals, you look back at your here, whether it's sine, cos, or tan, none are bigger than pi. So you're going to have to think about this a little bit. Now this one you can think about because you're finding tan of 5 pi over 4. So that's in what quadrant, 5 pi over 4? 3. Okay, so tan of 5 pi over 4 is in the third quadrant with a reference angle of pi over 4. So tan will be -1 here. Okay, so what angle gives you a tan of -1, right? So this is -1. So now we're going tan inverse of -1. So then, what tan ratios? Well, obviously 5 pi over 4.
-1?
But
Should be 1.
Yeah, it's in the third quadrant.
oh yeah, it's in the third quadrant. Sorry, +1. Sorry. +1. I was thinking cosine. So tan. So 5 pi over 4, third quadrant. Finding tan is +1. Now, when you're taking the inverse, when do you get a tan value? What angle gives you a tan of 1? Well, obviously 5 pi over 4. But what's a smaller angle that gives you a tan of 1?
Pi over 4.
Pi over 4. That's your answer. So you might say 5 pi over 4 to start, but you got to cross that out because remember, well, first of all, you can look here. 5 pi over 4 doesn't fit in there. Or you can remember your graph here, your y values. Remember this. If we choose 5 pi over 4, it's going to be up here, which is not a function with the other part. Okay. So you're going to want to find the smallest angle that gives that value of 1. Okay. So then here, this is tan inverse of 0. So looking at that, it looks like 0, right? And 0 falls in that range. So that's not going to require anything. You can think about it if you want, but what angle gives you a tan of 0? That's 0, pi, 2 pi, 3 pi, etc. Smallest is 0. right? So if these are inverses of each other, then it could be that value. But if that value doesn't fall into that interval that is the inverses are defined for, then you have to think about it more. Go up to the top here. So here you think, oh yeah, that's going to be 4 pi over 3. But wait a second, that is bigger than pi, right? Think about your intervals that it has to be. You can memorize those. I don't memorize them. I think, okay, 4 pi over 3 is here, right? So the cosine would be negative half, right? If I'm taking cos inverse of negative a half, the smallest angle that will give that would be up here at 2 pi over 3. Okay. All about those reference angles, right? So here you might look at it, oh, inverses, that's going to be 12 pi over 7. Wait a sec, that's too big. Okay, I don't know what 12 pi over 7 is. Sorry, cos of 12 pi over 7 is. But I know I can find out where it is. So that's going to be in the 4th quadrant. Right? So when you take the cos of that and then take the inverse, that's too big. Where does it have the same cos? In the 1st quadrant. What's the reference angle here? 2 pi over 7. So that's going to be 2 pi over 7. Smallest angle. Okay, negative, these are inverses of each other, so negative root 3 over 2 would be your answer. That's greater than negative 1, less than 1. All right, so looking at cos, that's good. Well, you can think about it if you want. Inverse cos, where do you get negative root 3 over 2? Well, a bunch of places, but the smallest one would be here, 5 pi over 6. And cos of 5 pi over 6 is negative root 3 over 2. Then here, inverse of each other. Okay, you think that? Does that fall in your intervals? Well, that is what? Negative 3 and 3/5 pi. Okay, that's more than a rotation, even in the negative direction. So, got to think a little bit about that one. So we're going, this would be negative 10 pi over 5, negative 15 pi over 5. So it'll be in the 1st quadrant here. Negative 18 pi over 5. Okay, so what's that reference angle in there? So that was, there's a 3 pi, so this will be 2 pi over 5. Okay, so knowing your reference angles, coterminal angles, is super helpful for this. You don't have to memorize anything. If you can think about, oops, sorry, I wanted to go back. Here. Okay, so let's generalize. So take a look. what these are. So this is sine inverse of sine of x. This is sine of sine inverse of x. Okay, so notice these. When will these be the same as what you started at? Okay, well, that's going to be the same here. For x in this case is an angle, right? So for what angles will this remain the same? So remember for sine, if you look back, that's your definitions up here, right? So that's going to be between negative pi over 2 and positive pi over 2. That inverse goes through, has to go zigzag through the origin for sine. Cos goes half a rotation, where is it here? So here, see how it kind of zigzags through the origin for sine inverse? This zigzags through pi over 2. Okay, so now x is the actual value. This is not an angle. So when is that defined for? That's for x between negative 1 and positive 1. And again, you can look back at that. You're not going to be asked to define what intervals. You're just going to be asked to calculate this. This is just a summary. You can even go, we could just do this actually. To help you. Okay, so now these are inverses. This is an angle. So now our angles, remember, for dealing with cos inverse, that's between 0 and pi. So it's going above and doing that zigzag above the axis. These are inverses of each other. This is now a ratio, not an angle. So that's between negative 1 and positive 1. Remember, these are your original ranges. In the inverse, they come to domains. Right? Your original range for sine and cos is negative 1 to positive 1. For tan is negative infinity to positive infinity. Inverse tan of x, so this is an angle. So remember, for the angle, it's between negative pi over 2 and positive pi over 2. And for the those switched around, tan of tan inverse x is the ratio, not the angle. So that can happen for any value. Okay, so notice how all of those questions were the same trig ratio, just the inverse of the original or the original of its inverse, right? Exactly inverse of each other. We take a look now at, there are some triangles. If you look at the bottom of that page, I have to flip over here, you'll notice that they aren't the same trig ratio. So there's a cos of a sine inverse, or a sine of a cos inverse, or a cos of a tan inverse. So they're harder because of that. So we have to come up with a way of getting a relationship between them. So we're going to use these triangles to help us. So they're all right triangles. We kind of forgot to put the 90s in there. Okay, and we're going to call this bottom angle theta in all of them. We forgot to label it. Okay, so what we've done for you is assign some values to some sides. So in the first one, the hypotenuse is 1, and the opposite side to theta is x. Here, the hypotenuse is 1, but this is the adjacent is x. And then this one, the opposite is x and adjacent is 1. So we kind of assigned the opposite and the hypotenuse for you, which is, in this case, so sine of theta in that diagram is x. Right? X over 1 is x. So if we were wanting to find what theta was, we have to take the inverse of x for arctan. Okay? So in order to do that, if we're asked to do that, so say we're asked to take the tan of sine inverse of x, that really means we're taking tan of theta. So then we can look at our diagram here and take tan of theta, opposite over adjacent, as long as we calculate what this side is. So right now you can see it asks you to determine an algebraic expression for each missing side in those triangles. So I'll give you a minute to do that. They're all right triangles. Back to mathing. Diagonal here. A squared plus B squared equals C squared. So this is a leg. Hypotenuse squared minus the other leg squared, square root. So they're going to be positives. Okay? I'm not taking plus or minus, right? These are triangles. So I found all those. This one here, so from this triangle, to come up with an equation that relates theta and x, I use sine, the easiest one. Same here. Adjacent is x, so I'm going to use cosine. So theta would be inverse cos of x. Or you can use arc cos, remember, same meaning. That's quite often use arc instead of the inverse sine. On this one, tan theta equals x, so theta equals tan inverse of x. Okay? So, do you have to memorize these? Not really. What you want to, first of all, you only need this information if you have cos of an inverse that's not cos, right? So different trig ratios in there, where one is an inverse. So I don't need those triangles for the previous questions we did. We want to get this relationship because they're not inverses of each other, right? It's a different trig ratio. So think about what's happening if I'm doing this one. You think of order of operations in here. I want to get what sine inverse of x is. Well, back here I said it was theta. Okay? So if I look at theta here, okay, that's this value. So this is really cos of theta. Well, in that diagram, what's cos of theta? It's adjacent over hypotenuse. Okay, so that is the value, cos of inverse sine of x is this. So, do you want to do all those triangles in a test? Because we're only going to give you, right, one of these probably, one of the other ones, maybe two, so you don't want to do that all the time. So what you want to think of, maybe I give you this one on a test, okay? So what I'm going to think about here is how to figure out this being equal to theta in a triangle. So then I think, okay, well, I'll draw a right triangle, and I want the cos of an angle to give me x. So cos of an angle to give me x would be that. So here cos of theta gives me x. So that means theta equals cos inverse x. That's that. So this is the triangle I want to use. Now to find tan, I need opposite over adjacent. So based on these in the Pythagorean theorem, the opposite here, this is this triangle over there, is 1 minus x squared, square rooted, adjacent is x. So I would just do this on the side. This is kind of like your work. Now, the next question uses cos inverse of x as well. So I've got that triangle here. It's this one here. Now I'm finding sine. So sine is opposite over hypotenuse. So that's just 1 minus x squared. Now get back there. Okay, let's look at the second column here. So now, this is on a test. You think, okay, I've got, these are different. I've got an inverse, so I'm going to draw my triangle. Here. Draw a right triangle with theta. I want the tan of theta to give me a value of x. Okay, so that means this would need to be x, and that would need to be 1. So here, tan of theta equals x, so theta equals tan inverse of x. Okay, that's what I want. So now, sine of that theta is opposite over hypotenuse. Okay, so I'm using this triangle here. So the hypotenuse, remember, is root x squared plus 1. So this will be opposite over hypotenuse. In these cases, we don't rationalize with the variables. So just leave it like that. You can even put 1 plus x squared. Sometimes they do that too. So because we often show it as 1, we leave it as 1 minus x squared. Even though we like that in descending order of degree, we also like having the first term positive.
Next slide, by x squared minus 1. Or I root x squared minus 1. Yeah.
Okay, so this tan inverse of x was from that same triangle. Now I'm doing cos. So cos of that angle is adjacent over hypotenuse. So that's 1 over root x squared plus 1. And again, I don't rationalize it. Okay, so then if this one was on a test, they're different, I notice. One's an inverse, but they're not both tan or both sine. So I draw my right triangle. Here, I want the sine of an angle to be equal to x. So sine is opposite over hypotenuse. So sine of theta equals x, so theta equals sine inverse theta. So now, in your triangle, what's tan of theta? Tan is opposite over adjacent. Well, this side here, so this is from the first triangle up there. This is root of 1 minus x squared. So this is going to be x over the root of 1 minus x squared. That's all we're doing on these inverse trig functions now. When you get to calculus, you'll do a little bit more with them. Okay? In Math 31, and then sometimes a little bit in Math 35 as well, if you're taking it to HL. Okay? Math 31 SO, you probably don't do much with that. Math 31 HL. Okay, so we're going to stop that. We're done that.